All right, let's see here. So I'll begin with a word of prayer. So get up here. Dear Father, we thank you for this day. Again, I thank you for this class and your creation. Help us to glorify you what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so last time I started talking about magnetic fields, and I told you that the net force in the presence of an electric and magnetic field on a charge Q goes something like this. Q times, E. We already know about that. That's the electric force, right? But there's a new one, which is the Lorentz. So this is all Lorentz force law right here, QV cross B. And so here B is the magnetic field that's applied, and the units for magnetic field are Tesla. And we derived that the force on a current you could write as the current times the length vector across the magnetic field, or if you prefer, you could write the length times the current vector across the magnetic field. So this is the force that a magnetic field places on a current. And then I also talked about if you wanted to go infinitesimal on this thing, you could say, well, the little bit of force, dF, that you get from a little bit of current flowing along a little dl, you could do I dl vector cross B. So this is the force on, we usually call this a current segment. Flowing in dl direction. Notice that the magnetic, that the force here is perpendicular to the direction of the magnetic field, right? That's what the right hand, the cross product does for you. So the first example I have for us that's a little bit non-trivial, example 1 here, concerns a current, not a loop, but a half loop. And so I'll try and draw a picture here. Example 1. Suppose you've got like this, and so I've got a current I flowing in like this, right? And what I'm going to do is describe like a little current segment that's at an angle, let's say theta here, all right? So I've got, let me use a different color. All right, so the magnetic field here is going out of the page. That's given. Let's see here, and I think I just used, well, these are really old. You got K hat here. So I usually use Z hat these days for out of the page. The magnetic field's coming out at us, right? So if I was to draw a picture of it like this, right? And great. The current, the dl vector looks something like this. All right, that's supposed to be tangent. I didn't quite succeed, but you get the idea. Now, what direction is the force then? I do what? I do dl, right? Crossed into B, out of the page, out of the board. So the force is that way. So my little df that we get on this little itty bitty current segment is, I'll eventually find a color I like in here. And maybe this one. Radially outward here, right? Did you guys see that? And so to find, what we want to do, my goal in this problem is to find the net force on the half loop here, all right? find the force on the half loop. Let me see if I've missed any other. Oh, I'm also given that the radius of the half loop is r. All right, so this distance here is r. All right. So let's see here. Can we break df down using trigonometry? Can you guys tell me? Like, what's df equal to here? So I think I could just use, I could write like this. I mean, I've done other things in the notes, but here I think I could just do this df times like cosine theta, sine theta. You guys agree, disagree, what do you think? Does that make sense to you? So that's a unit vector that points in the direction of f, right? That's just the vector that points radially like this, you know? So the magnitude's df, which we can get from that. So to be more specific, this is, what's my dl? It's r d theta, right? dl is r d theta. And so I can rewrite this as, I've got myself I, dl is r d theta, and then times the magnetic field, and then times what? So let me explain what I'm doing here. So what's the magnitude of df? Well, it's is equal to I times the magnitude of dl cross b, right? But how do you calculate the magnitude of a cross product? Do you guys remember? We do dl times b times what? Cosine? Nope. Sine, right? But sine of the angle, now not theta here, right? So let's say sine of alpha. Where sine alpha is what? Angle between the magnetic field and the dl. What's that angle? It's always 90, right? No matter where dl is, the magnetic field's coming out, right? So like that alpha is always 90 all the way around. So this is just I dlb, which is this. So that actually is the formula for the magnitude df. So we don't need anything else there, except of course this guy. All right? So if I want to find the net force, what should I do? On the half loop, it should be equal to, you know, the integral over the half loop, which is the integral from 0 to pi, right? Of IRB cos theta sine theta d theta. I might as well do both integrals at once. Do you guys know how those integrals go? Well, I guess we can work them out. So what you got here is IRB, integral of cosine is sine theta, evaluated from 0 to pi. Integral of sine theta is minus cosine theta, evaluated from 0 to pi. The first one's 0, right? First one's 0. And the second one gives me minus cosine pi, minus a minus 0, and otherwise known as 2. So there you go. The answer is 0, 2 IRB. that is the net force on the half loop. And of course, I've lost my B naught, so my bad. Let me add the knots back in. I'll do them in red. There was a knot here. Knot, 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 knot. I think I got all my knots. Yeah. Now, does this make sense? Do you guys see why it is that the x component of the force has to be 0? Do you see the difference between the x and the y here, right? So the force is like this, right? And as you're adding those forces up, the part on the left half of the loop and the part on the right half of the loop, equal, opposite, cancel out. The integration shows that, right? So if you set this problem up a different way, you could have argued by symmetry that the horizontal force on the loop is 0, and you could have just calculated the vertical component and constructed your answer like that if you wanted as well. Yeah. So this is just the way the math appeared to me today. If you look in the notes, I did it a rather different way. All right. So this is on page 83 of my handwritten notes. Any questions before I go on? Yeah.
I know you already said it, but why is sine pi why is sine 0 to 1 or sine pi 2? Sorry. My bad. Why is sine to the pi 2? Oh wait, sorry, that's cos. I'm done. Never mind.
Glad to help.
Yeah.
So
I had to work out my brain out loud.
that's okay. That's all right. Yeah, it's the sine of pi is 0, sine of 0 is 0, cosine pi is -1, minus of -1 is 1, and then there's another minus from FTC, which, yeah. So, but anyway, yeah. So let's see here. Next example, and this is a nice kind of test question, which is like, you can design a velocity selector. I might have talked about this already last time, I forget, but if you've got a charge q coming in with velocity v, right? And suppose you want to create some kind of contraption where the charge just gets through this particular region. Maybe you got some kind of gateway. You wanted to, the charge, and I'm drawing it too big. Think of it as point-like. There we go. There we go. So you got some kind of region, and you're trying to make it so that in here only velocity of a certain charge gets through. Well, then you think about, F equal to QE plus, QV cross B, right? If you set up the electric and magnetic fields in this region in a particular way, you can get it so that essentially the acceleration, you can make the acceleration 0, and so then that will just allow the ones with that particular velocity to pass through, and anything else is going to get deflected because the magnetic field and the magnetic and the electric force won't balance out. But if you had the force as 0, then it would just go straight through, right? So like, how do you achieve that? Well, if we want this to be, so if this is 0, for acceleration equals to 0, which gives straight path for q, right? Acceleration 0 gives straight path for q. How would you achieve this goal? So like v cross b goes which direction? Let's think through it. It's perpendicular to the velocity, right? So You know, I suppose you could think about this as like a big magnet, right? And we could set it up so that the magnetic field's going like this, all right? Just for the sake of specificity, we'll think of, let me stick with red. I'm using red for magnetic field mostly in these pictures. So suppose you set up the magnet so that your magnetic field goes like so. All right? And we'll make that a constant magnetic field in there. If you do that, what direction is, if that's my given magnetic field, I'm making velocity go this way, what direction is V cross B then? Well, we're going to assume Q is positive just to be, you know what, let's not. Let's be knowing. Let's say Q is equal to minus E, like that's the charge on an electron, right? If we do that, then what is the direction on this, you know, minus E V cross B? What direction does that go? Let's see here. So minus V goes this way, right? And then, yeah, into the board, right? Right, so we could say that minus EV cross B is parallel to like minus Z hat, for instance. So if we have that situation, how about QE? Well, QE is minus EE, also known as E. Sorry, I'm an idiot. But if you want that to balance out, if you want the sum of these two forces to be zero, which direction should you make the electric field go? You want that to be what? Out of the board, right? So you'd like this to be parallel to Z hat, you know, which suggests we should make the electric field what? Something like E naught times what unit vector? If we want to, suppose we're looking for a constant electric field to keep things simple here.
Z hat, right?
Z hat? Well, it's 50-50, so I'll go with it.
Those are good ups.
Does that work? So if we have that's, you know, minus I think we need a minus here. Because otherwise, so I need a minus here so that when I do, you know, minus E times E is equal to minus, I'm assuming E naught's positive, okay? Minus Z hat, which is what? E naught Z hat. Now that's parallel to Z hat, assuming that the electric field's positive. So I would like my electric field to go into the board. Because if I do that, since we're looking at the force on a negative charge, making the electric field going into the board makes the electric force go out of the board, right? And then that opposes my magnetic force. So I'm trying to walk you through like how you would set up something like this step by step, all right? So maybe in a problem that I would give you on a test or something, I would tell you, you know, suppose the magnetic field is set up like this and the velocity of the incoming charge is like that. And then the question would be, what direction should you make the electric field go in order to, you know, select a particular velocity by making, you know, building a velocity selector, which for us means that the acceleration is zero in the region where the fields are. And if this is all the case, then what particular value for E naught do we need? See, what we need is we need minus E well, let me just say it this way. We need the magnitude of QE, right, to equal to the magnitude of QV cross B, right? So the Q's cancel, and you can see what we need is E naught is equal to VB naught, right? So you should, well, that's it. This is the choice where V is speed, of course. This is the electric field you should use for a given magnetic field B naught, right? Probably you have more ability, a lot of times you might have more ability to adjust the electric field. Maybe the magnetic field is like a consequence of a permanent magnet. You can't adjust that, right? It's just a property of the particular permanent magnet that you have in the region. And so like this, you might be stuck with this, but you're able to adjust the E naught by essentially changing the voltage on two capacitor plates, which set up a constant electric field between those plates, right? You could imagine this. So that's the velocity selector.
Question?
Yeah, go for it.
Where's that relationship, magnitude Q field is equal to magnitude Q V cross B?
Oh, this is if the net force equals to 0.
Wouldn't we need a negative on one of them then for that, though?
But, well, yes, but the magnitude has to be, they have to be equal. I mean, yeah, I mean, fair enough. You can, I mean, wherever you want it, we can put it here.
Yeah, that
But,
makes sense. I was just like,
but,
I don't.
yeah, well, exactly. So, but you're absolutely right. In terms of like the vector analysis, they have to be, one has to be the negation of the other to add to 0, for sure.
How you set it up, V and B are perfect.
Yeah. Oh, yeah. That's the other thing is like the cross product is just a product. But I'm sure we could come up with more insidious versions of this problem where the magnetic field and the velocity were not, perpendicular. But we're trying to design something in a simple way, not in a more complicated way. So let's stick with this. So the torque on a current loop, I should talk about that for a minute here. So I think I walked you through how that happens in terms of the force on the, each current segment. But I'm just going to give you some nomenclature, some usual definitions, some quick formulas, if you will, for these sorts of problems if you come across them. So for a current loop, looks something like this. So example 3. And I just draw the loop like it's a square, but of course the square could be a circle. It doesn't have to be a square, all right? Like it literally could be a loop. So I've labeled these different segments like I1, I2, I3, I4. Anyway, the point is that they're all equal. We're talking about a current loop. And then, but that doesn't quite do it justice yet because, so first of all, here's like n hat. This is normal to the plane containing the loop. And also, the thing that I haven't really captured into my picture very well, but maybe I should actually just trade my picture for like something like this, because it could be like this. N-fold loops. All right. It might be better to actually think about it like that. All right. And in this situation, if there's a magnetic field applied, and you got this loop of current, and you apply a magnetic field, it doesn't have to be any kind of nice way. It could be like this, perhaps. I'm sorry, I have violated my color code for magnetic field at the moment. You'll forgive me. But anyway, the torque, which is a vector, is equal to mu cross B. And I'll define mu in a second here. Mu is equal to n, mu vector, N for the number of loops, I for the current flowing, and A for the area of the loop. And n hat is its direction. And basically the way it works is the more loops you have, the more torque you get, right? Because you get a doubling. If you have 2 loops, you get double the current effectively interacting with the magnetic field. If you have 3 loops, thrice the, the torque and so forth. And the bigger the area, the larger the moment as well. So this formula works for squares, but also for honest to goodness disks like this. And what's torque? Do you guys remember?
Defined mechanically as the lever arm across the force, right?
Defined mechanically as the lever arm across the force. Yeah, okay. Sure. So torque, remember, we could do I times alpha. I guess I can do I times alpha vector. Now, but, okay, so for us, we insist on, essentially one-dimensional rotational motion in this course, which means that we're only going to entertain torques which happen to align with the axis of rotation, right? Because that's the only place we can do the math without getting into the full inertia tensor and all that junk, which we don't know about, so we don't do that. But we do write, the moment of inertia. Ooh, unfortunate. Inertia. So like, this is the inertia tensor times d omega dt would be equal to, NIA times the magnetic field, assuming that, of course, everything is aligned so that the cross product is maximized. So if you were given a current loop and a magnetic field, and you were told the actual moment of inertia of the loop, then you could actually figure out what's the angular acceleration, how fast would it actually make the loop spin and so forth, all right? So
You should
cancel the eyes. Yeah. I need to dress this one up. Nerd. The inertia, not the current. All right, enough about this. Moving on here. So that brings us to our next topic, which is the magnetic field due to a moving charge. So this is known as the Biot Savart Law, and it is, again, as everything seems to be with the magnetic field, it will drag us into, whether we like it or not, a discussion of the cross product. All right, so I'll leave these up here just for comparison. But the Biot Savart Law, well, as before, we're going to do it for a point charge, and then we'll level up to a current. All right, so here it is: magnetic field due to a moving point charge. So let me just kind of explain the difference philosophically between what I'm about to do and versus what I've been doing before I do it. Up to this point, I have talked about magnetic fields, but I have not explained where they came from. I just told you there was a magnetic field, and here's what it does to a charge, right? It produces this perpendicular velocity-dependent bending force, right? I didn't explain where the magnetic field came from, though, did I? I did not. So at this point, I will start confessing to you how magnetic fields arise? It turns out magnetic fields arise from moving charges. And in particular, this is an experimentally determined law, the Biot Savart law, but here it goes. Mu naught over 4 pi q v cross r hat divided by r squared. I'll draw a picture here. I'll try to draw a picture here. So we've got a positive charge q, and its velocity would be like this, and I'm talking about the magnetic field over here at this point, all right? And so this distance from the charge to that is r. So the r hat vector points from the place where the charge is to the place where, you know, measuring the magnetic field. And the deal is I do v crossed into r hat. What's that do for me? V into the page, right? So here the magnetic field would look something like this, all right? That is the magnetic field due to Q moving with velocity v at, you know, distance r from this point. All right. Now, mu naught is yet another fundamental constant of nature. Mu naught, here it is, mu naught is equal to 4 pi times 10 to the minus 7 Tesla meters per, I think that's amperes. Or if you like, you could write this as 4 pi times 10 to the minus 7 newtons per amp squared. Okay. All right. Now you might wonder, does this thing have a name other than mu naught? It does. So this is the, where's my marker? Do you guys know what it's called? Anybody? Well, let me remind you. I'm not going to tell you the number for it, but I'll remind you the name of this. Epsilon naught, this is the so-called permittivity. Permittivity of the vacuum or empty space. This guy right here is the so-called permeability. Permeability of the vacuum. As you might probably guess from our discussion of linear media, you know, you can talk about the permittivity of various linear dielectrics, and you can compare those to the vacuum, right? There's exotic materials which have high choices of epsilon, which make for good capacitors, stuff like that. Talked a little bit about that. And likewise, you can have materials that have other mu naughts other than mu naught. But I don't really think we do much in here, but you can talk about permeability of some other material. But mostly leave that for another course. Anyway. Okay, so this is the Biot Savart law. But we oftentimes need the Biot Savart law for a current segment. So what's the Biot Savart law for a current segment? Well, here's what that looks like. So if you can imagine a current flowing like so, all right, and right here you think about the infinitesimal, you know, line segment going along the current like that, and then you ask, okay, so at this point out here, at this point P, what's the magnetic field do to that current that's flowing right there, that little segment at least. Then you need to calculate the distance from here to here, which is going to be R. All right, and so what I'm trying to figure out is describe the magnetic field at P due to I flow. And I'm just calculating the infinitesimal contribution due to just that part of the current, just that little dl. All right. And so here, if I draw the vectors down here, I'd have dl goes like this. I have my r hat goes like this. And the dB, right, is going in the dl cross r hat direction. So dl cross r hat. So, up to the limits of my artistry, the magnetic field, the dB, goes like this. And the formula for it is simply going to be mu naught over 4 pi times IDL, and that's a vector, dl vector, cross r hat divided by, well, r squared. And so to find the total current, to find the total magnetic field, we have to integrate this over the, the current flow to find the magnetic field at P. All right? That's what we'd have to do. So obviously this takes a little bit of effort to work through for non-trivial examples, right? And so I think well, I guess I probably can do this one. I was going to get the projector out, but I think I will resist the urge to get the projector out and do one more example by hand for the moment. I do have some more insidious examples past this, but we'll get to those next time. All right. So let's see here. So what I want to do, my example, what am I on, 4? 5? I can't remember. 4. So example 4, we're going to find the magnetic field due to loop of current. All right, so, and I'm going to try to stick with my picture here if I can. Oh man, whale. Not sure I want to do that. Funny. So I want to find the magnetic field at the center of the loop. I'm just debating how I want to draw this loop, guys. So I'm going to draw it this way, different than the notes. I might get stuck, but we'll find out. We'll figure it out together. So I'm going to draw the loop like this, all right? And I'm going to make the current flow in this direction. All right, so here's the center of the loop. I'm trying to find the magnetic field loop current at its center. All right. Center point. That was supposed to be the center. It looked like, I guess that, I don't know. Anyway, so there are a bunch of right-hand rules to learn in physics too, all right? And we're starting to enter that part of the course. Where there's cross products, there is right-hand rules. So here's one of the right-hand rules you should know about. If you got a current loop, what you do is you take your right hand and you imagine wrapping your fingers around the loop. All right? Not like, but like encircling the way the current's going. Your thumb will point in the direction, the magnetic field that it creates. So we're gonna find out that the magnetic field, it's gonna be like upward like that. All right? But let's not, I'm just telling you that's like what's gonna happen. Let us derive it. And the way to derive this, of course, is to, I mean, we should probably just, let's see here. I'll attempt a picture. So here's my like DL, right? And how is R supposed to point? R is supposed to point from the current source to the field point, right? So R point is the center-seeking unit vector like that, right? Those are perpendicular. Use your imagination. Okay, so DL crossed R up, right? Now I come over to here. Here's my DL over here. My R, that's supposed to be center seeking. All right. DL crossed into R. It's still straight up, right? Doesn't matter where you imagine yourself on this loop. Back here, DL R hat directly, right? Again, DL crossing the R straight up on the loop, right? So no matter where you imagine the current segments, they're all giving you a little dB that points what? Straight up, right? You see that? So when we add these up, we're going to get a net magnetic field that's going up. Okay, so what's the formula in this particular instance? I'm just going to focus on the magnitude because we know that it's going up. All right, so dB is equal to mu naught over 4 pi. Now what's my DL? DL we can write as r d theta. I guess I should have told you the radius of the loop. That probably matters, right? So DL is r d theta. So I've got I r d theta. And then r hat's a unit vector, that doesn't matter. And divided by r squared. Also, there's perfect symmetry for this loop, right? Every bit of the loop is contributing the same amount of magnetic field as any other part. There's a perfect symmetry all the way around. So the integration here is going to be very easy, right? Because we can see that the net magnetic field is just going to be the integral, you know, from 0 to 2 pi of mu naught I r d theta. I didn't even simplify anything yet, guys. 4 pi r squared. What happens here? R's be canceling, and so you just got mu naught I times 2 pi divided by 4 pi r, right? So we get mu naught I over apparently 2r, I think. So the magnetic field is simply B is equal to mu naught I over 2r, and and we'll say with n hat given by the right-hand rule that I described at the start of this example, right? So again, encircle, put right hand, imagine going around the loop, wherever your thumb points, that's the n hat. So if we made upwards z, this could be a z hat, whatever, but that's the magnitude mu naught I over 2r. So this is the magnetic field due to a current loop at its center. Notice that this is special to the center, right? If you move off the center, the calculation becomes much worse, right? Do you see that? Because if we're not at the center, we don't have that perfect symmetry. We'd actually have to do the integration all the way around. And we'd have to think through this pesky cross product And we'd have a lot to process. And we'll process those kind of things next class for some examples, okay? But that's it for today. So, thank you guys.